Very good guys.
Anyway, this is Favonia, and he's going to tell us about computational high-dimensional type theory. Thank you.
Yeah. Thanks for coming this morning. It's even like earlier than usual, and I appreciate that. But the benefit is that then we can have the lunch soon. Okay, so I'm going to present. So I changed the title to include one more word because I also talk about the implementation we are working on right now. So I'm going to present the computational high-dimensional type theory, which is being worked on like very actively by our group recently. So I joined this right after my thesis. So okay, so let's move to the real content. So I want to spend a little bit more time on the idea of computational type theory a little bit because it's actually different from many type theories you know of. So please bear with me. Now I'm not just talking about type directly, I have to talk about something, the framework. So we start with computation, that you have a notion of programs, and you know how they compute, and you know what are values, and so on and so on. And once you have set up that, so you can have, for example, in the history, people have been using natural numbers, like by cleaning realizability that they use natural numbers as a program. Well, we are like, now it's in the modern age, we are using untitled number calculus. But nonetheless, you pick something as a programming language. And then once you settle it down, then you prove some theorems of it. You have a framework to prove properties about the programming language you define. So this is very similar to the Martinov's, oh, I think it's a little bit too bright. It looks fine on my screen. Anyway, so it's very similar to lots of things that have been discussed in Martinov's work, where he has a meaning explanation, and then trying to then write down rules that make sense in his meaning explanation. So there's an analogy here. I don't want to say they are the same because in Martinov's philosophical work, these are pre-mathematical. So it doesn't mean that you will have a formalization. So we kind of pick a particular way to make it mathematical in some sense. But if you allow yourself to say that, okay, now I recognize the programs as the pre-mathematical object, then you probably can just apply the same thing. But at the very least, I think there's an analogy here. Oops. Okay, so so we are now like using, as I said before, using an untyped lambda calculus or unitype lambda calculus. This is Bob's favorite. As the programming language, as in Newpro. Oh, I should fix the capitalization. I think now they are using the uncapitalized PRL. I think it has been changing all the time. I keep confused. Okay, so A and B are equal type if A evaluates to A prime. So all of them are terms. The one of the term in the programming language you just defined. So you evaluate A to A prime, and then you evaluate B to B prime, and we say that they are the same type if they recognize the same value. So you actually have to write down the meaning of the A prime and B prime like in your mind. I will give you examples later on. So this is just a framework. And we say that M and N are the equal with respect to A. Is that, for example, A has to make sense because otherwise we are not able to talk about membership in A. So A has to be a type. Then, so you might think that why do we even have to talk about A equal to itself? Well, because this is a partial equivalency relation. So actually it means something when I say that A is equal to itself. All right, so it means that A is a type, and then we want to get that value. And also we evaluate N and M goes down to values. And as I said before, that being a type means that we know what kind of values are inside of that type, and also what kind of value are regarded as the same in that type. So now I just ask the value, the A prime, like, are they the same? And if they are the same, then they are the same. Does that make sense? For example, we can say that bool is a type because in our programming language, you just throw in the syntax bool, and you say that it's a value. So it will evaluate itself. And then we also have to write down the meaning of it. So so bool recognize true and false as values. Oh yeah, so in your programming language, you also have to have true and false. So they are also values, and if you say that they are values in bool, so that satisfies the definition. You can then say that bool is the same as itself as the type.
And when you say same values, there's some, like, one thing is like, you mean closed values probably, or values that contain variables in them?
Here I'm only talking about the closed judgment. The open judgment is usually defined by considering all the closed substitutions.
And my recollection, like from Newport, was that equality is somewhat coarser, that like two functions that are not the same but give the same results for same input are also like equated, or like you have functional extensionality or that sort of thing.
So it all depends on how you write down the semantics of the types you want to say. For example, you can say, I have a function type, and I recognize all the extensionally equal functions. Yeah. Then that will be a true.
But here, when you say same value, you mean like extensionally equal value, or?
No, you define your own notion of sameness.
Okay.
You write down whatever that you want, and then you have to prove.
So you have an untyped notion of sameness, and once that's in place, then you can define when two types are equal.
No, the A prime here, for example, bool, for bool, then you write down the meaning of bool. Here is simple, that it's just true or false. But for functions, you can then say that if you want them to be extensionally equal, then you write it down saying that the two functions are related if they are extensionally equal, and also they make sense as functions.
But shouldn't types be equal only if they have the same equality? You're saying types are equal when they recognize the same values.
Oh,
but they should also recognize the same values as identical.
Yeah, so they should recognize the value in the same way. If two things are equal here, and two things should be equal here. Yeah, good catch. I tried to compress the technical explanation in 2 lines. I think I compressed too much. Yes, you should recognize the same way and also recognize them in the same way.
Equal partial equivalence relation.
Yeah, it's an equivalent between two per being equal. Let me give you one more provocatory example. This is perfectly fine as a bool. Okay, let's suppose that you have natural number. So it doesn't seem well typed that 2 branches doesn't have the same type, but it's fine. The reason is that this, as I mentioned before, we always evaluate it first. So this will evaluate to false. And the false, according to our definition of bool, is in the bool, so it's fine. So this also shows that actually, this is not really the ETT that you might have in your mind, because in ETT you are not able to prove this is in bool. The 2 branches are now of the same type. Okay. So actually I have to, in light of that, I actually have to clarify something. Before that, let me talk about our motivation. So why were we doing this? Like, given that Newport is already there and there are lots of cubical type theories. Well, the hard, as I said, the hard and the situation system seem to have the higher dimensional interpretations. The Newport only know sets in something. So it doesn't have the like circle, it doesn't know path, and so on. So we want to have an extension of it. So what we want is we want to have the realizer and programs, but we also want to have all the extra stuff that is currently now in the hot community, that you have the dimensions, and you have a collaboration, you can compose things, you can do coercion, and you also have interesting spaces like the circle, the suspension, maybe torus, and other colimits or something like that. And we also want the con-universes and univariants. So basically we want all of them. And we want to see whether we can extend the original neutral realizability to account for all the extra things that people have been working on in hot. Make sense? Okay, so I want to talk about it, but really there are lots of confusions about the computational type theory, so I have to clarify them a little bit. Oh, actually, seems I don't. Let me there's one slide for this, and I promise I'll go to the clarification. So why do we want to do this compared to other type theories? So the equality here, I just told you, is closer to the equational reasoning that you probably have in other type theories. So you have functional externality. Well, now many type theory also have that. But we have 4 universal properties. What that means is that, for example, if you want to prove 2 things are equal, like 2 functions from net to net are equal, then you are allowed to use the induction principle on net to consider the 0 case and 1 and 2 and so on. So this is not the case in many type theories. I will go into a bit more details in the future slides. So the next thing is that we have a realizability. We work with realizability directly. So adding more theorems will not ever destroy computation. That you will always have a programming language. You just prove in new theorems. So remember the picture that is that you have a program here, and then you try to establish a theory for these programming languages. The programming language is still the same, and no matter what kind of theory you established. So you will always have a nice properties, but unless you screw up the programming language, I guess. But pick a reasonable programming language, then you will always have those good properties. All right. I think this. Okay. Yeah, this is the clarification that I've been waiting for. This is very exciting, I promise you. So the first thing is that the thing we are talking about is not extensional type theory. So realizability, or realizer can form a model of ATT, it can form a model of ITT, and it could potentially, we didn't prove it, we're still working on it, but potentially be a model of a HOT, the book HOT, or other type theory, but it itself is not the ETT. Like, because none of them has a realizers, none of them has a separate programming language that you can work on. And in fact, you can, given the same programming language, you can prove whatever your theorems that you want to prove and collect them as rules and create another theorem. And then our realizers will be a model of your favorite theory. So what my point is that they are really like oranges and apples, and they are different.
Can I ask another question here? So this is like against my conception of NuPerl, which I tried to build. So my understanding was that in NuPerl the realizers are actually untyped computations, right? And then so the types define these partial equivalence relation, as it were, on the like in Stewart-Allen's model. Anyway, so if the realizers are untyped computations, how can they be model of ETT, ITT, or whatever? I mean, they are just untyped computation.
By model, I mean that you present a way to it's a how do I say that? So you interpret the rules in a particular way so that they become theorems that is provable against the realizer. So you're creating a realizability model.
Anyway, a conceptual way of thinking about it, I don't know whether it will help, but I mean, if you start with the programming language of realizers, maybe there's more to it than this, but you can form a realizability topos, right? Using that, and so that's and actually there's a model of constructive set theory there because it's a realizability topos cumulative hierarchy. We know how to do things like cubical sets constructively now because of Thierry, so you could interpret, or you could make lots of different categories with families inside that topos in various ways, modelling various sorts of type theory. Is that what this is? I don't know, but I'm hoping to find out.
It's just the wording here that the realizers themselves are already a model of ETG. That's what it says here.
Yeah.
What I'm happy with is like from the realizers via some of the realizability constructions, you can build models of various systems that yes, but that they actually are. That then looks more like typed realizability or something. And I don't know whether you have that in mind.
Well, being a model doesn't mean that everything the realizer, everything in the programming can be typed. You can add more things that don't make sense.
So like induces a model or something.
Yeah, I can just put a smiley face or emoji icons in the programming language, and that's fine, as long as you don't change your theory in a crazy way. Actually, I really want to do that. Unfortunately, the Unicode support is not very good in standard, but okay, that's it. Separate issue. Because the realizer of the void, the empty typing is arbitrary, right? But anyways, all right. So let me continue the real stuff. And there's the second clarification that the being computational doesn't mean that in our setting doesn't mean that you have operational semantics and canonicity. They are different. Let me show you one example. So I'm now assuming that most formal, by formal I mean that it's not being computational, that it's starting from programming language. They really want a decidable type tracking. Actually, I think that if you don't want this, or if you don't care about this, I don't even know why you want many. I think that the main reason, the reason that you want several type related because you want the decidable type tracking. Anyway, so let's suppose that you want it anyway. This judgment is in general not decidable because you have to consider all the inputs from natural numbers, and but there are infinite number of the natural numbers. But this can be proved by induction on the inputs in our setting. If you define the meaning of errors in the right way, then you can use the induction on the inputs as if you are just proving a theorem about realizers. So this can sort of be done. So my point is that even if you have a rule and you prove the established operational semantics and you prove the canonicity, you still cannot do this. This is fundamental because there's a design choice. Now you want the type checking to be decidable, and you have to rule out all the non-trivial type checking. For example, this one. That this involves the non-trivial mathematical induction that is in general cannot be done automatically. So you have to prove that. So even if you have a good operational semantic, I claim that they're still different. So that's why I say that the undecidable rule has to be entirely thrown out of the window. But in practice, actually, it's not, like our system is not as far from the system you might have in your mind. So, for example, in code, that you are using tactics and to refine the goal, right? And this is a similar thing happening here. That you might be worried that, okay, if now I'm able to equate two functions from net to net, how does the machine is going to check? Well, the machine will actually just ask for help from the users in the real system. That if you want to establish like whether the two functions from net to net equal, you'll ask you what kind of induction that I want have to do here in order to say that they are equal functions. So it's kind of that it's really similar to the tactic-based or many interactive system that if the system cannot figure out something, we'll just ask it. And if you're fine with this, then actually there's no problem of having the seemingly undecidable things in your system because the system will just ask you. Does that make sense? All right. So I haven't talked about the being cubical yet. I'm going to a higher dimensional. So now I'm going to introduce like how exactly we have done to the programming language to support the cubical features. So this is done by Carlo, Bob, and Todd Wilson. So Todd Wilson visited CMU at one point and worked with us. Okay, so there's an interesting thing now. We will also have dimensions or interval, no. I think we'll have dimension as the CCHN that representing the higher dimensional structures. But we are different from CCHN in the sense that we don't have a connection. So the expression can only be 0, 1, or variable. So it's the same as having the index category as the Cartesian cube. Yeah, Cartesian cube category, but it doesn't have like connection or other things. Okay, so let's begin with a circle. This is the simplest motivating experiment I can think of. So the circle is conceptually defined as a point and a loop. And let's create a programming language to program with it. So first of all, you have to say that there's something called circle. All right, this is, I think, and then also say that this is a value. All right, and then you want to say that there's something called base that is also a value. So you can say that base in the circle, for example. And what's next? Oh, loop. So loop is the interesting one because now it has mentioned a dimension. So the loop is taking a dimension expression. And the meaning, I think the meaning actually is more vivid when you look at how they reduce. So loop X means that the loop is occupying some direction, and in that direction is a path from a base to base. And when you go to one of the endpoints, then you becomes a base. Does that make sense? If you have been working with the CCHM system, I don't think any of this will surprise you. Okay? And so these are the formation corresponding to the many type theories. So this look at the formation rule, and these are like the introduction rule. And so we also need something like the elimination rule. So which is S1 lim. So S1 lim is taking the motif you are trying to prove, the theorem about the circle you're trying to prove as A, and then you're taking M as something that should be something in S1. I keep saying should be because everything is untyped, that it could be complete garbage, but the intention of this construct is that you should put something reasonable as N, for example, base. All right, so in the capital B and L there is the proof you provided in the base case and the loop case. So, for example, you keep reducing M and N prime till they reach the value. And now if it's a base, then you reduce to B, capital B, because that's the proof you provided for the, actually, I shouldn't say proof, I should say realizer. You should, as a realizer provided for the base. And if it's a loop, then it's taking a variable here. Otherwise, it won't be a value. If it's a value, then it's taking a variable. And then you just do the substitution here, removing n. Does that make sense? So now you almost have a circle, except that it's not count yet. We also want to make sure that it's a count. I don't even have to I haven't even talked about count yet. So we'll work on circle later, but I have to talk about what we mean by count. So count in our framework had two parts. So one with the coercion and one with the homogeneous composition. So the first thing is the coercion, which is simple. That if you have a type that makes sense along the dimension x, and you have something, for example, you have something in the 0 point that you have an n in the 0 part of the type, and you want to coerce it along this type line to the other end. So we write down the notation as coercion of from 0 to 1, and it's taking a type that makes sense for arbitrary x, and then it's starting from n. So the general notion is that it's a coercion from R to R prime, and you provide m, some m here, and the result should be in the destination. So I keep saying should be because everything can be complete garbage. But I'm saying that if everything is well typed in a serialized way, then you should fit in something that here, and then the result should be like that. And being a count, part of the condition of being a count is that you should implement this operator correctly. All right, so this is coercion, and then you will have a homogeneous composition. I hope this is not so surprising if you already have seen some empirical type theories. So this H comes from R to R prime again, and then it's A is homogeneous, so it's not taking any variables. And then you have M as a cab, and now for each additional extension extension, we also put in a pair of cube there. So this is a very restricted form of the system. So you can, like, if you translate it into a CCHM system, this means that this equation from x equals to 0 mapped to this cube, and x equal to 1 mapped to this cube. I want to make some comment about why we want to separate them, because in the CCHM there's also just one single count instead of two separate operators. The separation is for canonicity on points. I'm not able to go into the details at this point, but the decision now we only have this very restricted form of the system and have a separation of the homogeneous count and COI is for canonicity on points. Unfortunately, I'm not able to go into the details in this talk, but we can talk offline if you want to know why that this is the case. In particular, we forbid empty systems. If you have been in the MRC at the beginning of June, you know that we try to compute the Guillaume's number, which should be just 2, but it's so difficult to compute. You end up with lots of empty systems that are in the middle of the stage. So we forbid that. The reason we are able to do this without running into any kind of regularity issue that it's very difficult to handle with is because of this separation and this restrict form of the system. Again, I'm not able to talk into the detail why this implies that, but we are able to do this. Okay, so with this, we also want to complete our circle construction. Our circle is not count yet. So how to make it count? Well, first of all, we have to implement the COI, what the work COI should do on circle. For circle, it's actually trivial because the circle is a constant type. So you do nothing, you just get it send and out. So that's a rule. And for HCOM, homogeneous composition, so it should compute in several cases. The idea is that it should compute as if we can compute that, and if everything is stuck, then it's a value. So this is the first case I should compute. For example, is R to R, the beginning and ending are the same. And you are doing the composition from R to R prime, then you should just get a cat back. And if one of them, if one equation is true, then you should step into one of the two. Yeah, this is a little bit tricky to write it down formally, but the idea is that if one equation is true, then you should step to the two. If none of them holds, if you cannot go to the cap, if you cannot go to any of the two, then we have it as a value. Does that make sense? Alright, so this was fine, except that now we have a value. And our elimination, the S1 elim, should handle all the values. So now we have base and loop and this new kind of value because we don't know how to deal with the HCOM. Yeah, so this needs to handle the new values. So this is a little bit complicated, unfortunately. So the HCOM in the domain will become the the composition problem in the codomain. I'm not able to go into the detail here, but it's basically using a heterogeneous composition in the codomain when by basically, so M will become, how is it? So the cat will become cat with a B and W dot L, like giving the same data and trying to just form the elimination form there. And you do the same thing for every tube here. So every tube will have the form S1 elim of the original tube face and the same B and the same L. So you kind of delay the problem to the, push the problem to the codomain. Yeah, I'm not able to get into detail, but I just want to convince you that yes, this is doable. All right, suppose you believe me that this is doable. So now we have a count circle. There's still one like tricky stuff I want to bring up is the cubical stability, and this is actually I think the one of the trap that you will step on if you try to like working on this. You have to. I think it will take you some time to get used to this. So what I mean by that, so you have a S1 elim, so this is the elimination, and you are taking a loop, and it's a B, right? And according to our semantics, you step to L and with the renaming. What if you then you want to do the substitution? So you substitute 0 for X and for L and 0 for W, right? It looks fine, except that if you do the substitution first, then it might not be the same. So for example, if you do the substitution here, 0 for X, let's suppose that X does not appear in B or L. And this will go to base, and with the same B and same L. And according to our operational semantics, this will go to B. And since all of them can be garbage, there's no reason to believe that these two will be the same according to our semantics. So this is actually a new phenomenon when you go to the dimension variable. Oh, sorry, when you have the dimension expressions. Without a dimension expression, for example, in Newplot, the substitution always comes with the computation. That there's no strange interaction between the substitution and the dynamics. And now suddenly, that if you substitute something first, and it will affect the dynamics. And if you have a value, for example, and then you substitute some of the dimension into some 0 or 1, maybe certainly it's no longer a value. So actually, let me go back the slide here. For example, they might not be equal under this one, and by being not equal, it could be that there's a variable x and y, and I can substitute them with the same value, and certainly then it's no longer a value because you can then apply one of the rule to step into something else. So this is a really difficult thing to handle with, and to handle that, we actually need to talk about the cubically stable type. That the types not just make sense now, but also make sense under any kind of substitution. So we have to quantify it, like in many places, you have to quantify over all possible substitution, because otherwise the theory is not even close under substitution, and it doesn't really make sense. So the trick is to consider every substitution. The technical details is very messy, so I'm not able to show that, but let me give you some theory. So basically, you're putting the stability condition everywhere. So this was the definition of the two types being equal here. So the first thing is that, yes, you need to have the constructor, but also in every part, it had to be stable. That is, like you work well with the substitution. The details are really, I'm not able to fit all the details in this slide, so you should just, I'm sorry, but you should just look at the papers, I think. And also the meaning that two terms being equaling A or stably equaling A, that you should also have this, all the additional technical constraint to make sure that the substitution will not affect this. And then you have a reasonable proof theory. Or that, all right, so this is my very short introduction to our framework. Compared to the CCHM, so we are based on the realizability. So we have our notion of equality is closer to the standard mathematical equality. For example, I believe if we got the universe down, we could probably internalize the simplicial types. It could be possible, but I didn't prove it, so I don't want to make a strong claim. And we don't have connections, and we don't have empty system, but in some sense, it's kind of handled by the specialized composition problem and coercion there. These two, right now it's like a choice, like just a taste, but I think in practice can also make a differences. Because if your goal is to compute the Guyon's number, for example, without the connection, without the empty system, I think you'll end up with a much shorter term to deal with. Having a connection, that means that your system is more complicated, and you have to come up with some way to handle it. Now we are working a very restricted version. I only have an equation. Like for implementation wise, I think we thought that the fact that we don't have to deal with the connection is really like save us lots of trouble.
But I mean, is there any real technical reason why not to consider connections? I mean, after all, Thierry and his co-workers moved from the first cubical model to the second one with the Morgan algebra with connections. It certainly made a hell of a difference to how easy it is to prove you have a univalent universe, right? I mean, for example, it must make some things easier to do.
Yeah, so this is a little bit awkward because we don't have the universe working out yet.
Yeah.
So
that's one way of avoiding
yeah.
whether it's wrong. But is there a technical reason not to have a more structure on the syntax of dimensions than just 0, 1, and variables?
I think in theory it's also an interesting question whether you can do all of this without connections, because category in some sense, or I think the minimal you can have almost.
Yeah, well, you sort of put less in there, it means you have to work harder somewhere else, but.
Yes.
Yeah.
Yes.
Yeah.
Right. Okay. So let me continue. Let me go to the next slide. So the current progress is that we have a dependent function. By done, I mean that we write down a reasonable semantics and we prove that it's a count type. So you can do composition and you can do coercion it. And so you have a dependent function, dependent pairs. You have strict rules in the sense that all the composition in the strict rule will reduce to true or false. I only recognize true or false. Everything else will reduce to that. And we have weak rule, which means that you have a formal composition at each count standing there. You have a circle, as I showed you before, and we have and we have lots of other things. And we also have the univariate for strict isomorphism, which means that the proof that f composed with g is identity function needs to be exact. So if the two functions satisfy this property, then we do have a univariance for that. So what we are working on right now is the four univariants that work on any equivalence, so not just the strict isomorphism. And we also want to and with this and then have count universes. So with this and then we can claim we have everything. We are still trying very hard to work on it. So this is the summary of our progress in the theory part, and now I'm going to the implementation. So I'm going to live demo part of it. So this is a proof of system. Yeah, I can talk with you more about why this name Webflow, but let me not go to that part now. So it's a proof of system based on the theory I was just talking about. And it's not only an implementation of our theory, we'll also try to incorporate some of the recent advances in the refinement theory. So one of them is, if you've been using calc until version 8.5, I think, you're not able to have a dependent subgoal. If you want to establish a term in the sigma type, it's really not easy to use tactic in the way you want it to be. And this is, so Springwalker thesis kind of addressed this problem, and it's already in a stable version of the 8.5, I think. So we kind of did this, and John and Bob established an algebra inspired by this work, and then we implemented it in the Webflow. So you can have a dependent subgoals. So if you know Nupro, the constructor of the dependent pair in Nupro, that you have to feed in the first component when at the moment that you're trying to use the sigma type. So the way to prove the sigma type is that for magical reason, you already know what the first component is. And then you prove that there's a second component. The reason is that they don't really have a dependent, they're able to talk about dependent subgoals. So the way to erase the dependency is that you provide anything that can possibly depend on in the tactic. So the calc was also like that, and then it changed to unification, and finally it has dependent subgoals now, and we also have dependent subgoals. So this is just one example that we're trying to look at the recent events in the refinement theory and try to implement them as well. So it's changing every day. I think I just added some numbers last week, but we already have something that I can demo, and so the thing I'm going to demo is it's kind of address your issue in another way. So even though we don't have the connection in the index category, we can still prove that there's a square, satisfying all the edges. Okay, so let's do this in Nupro. Okay, so we have a hook. Is that large enough? No. How should I change the font? I'm not really Emacs.
It's a Windows machine.
What? Oh,
Control X, Control
We,
plus.
we only know the key.
Control X, Control plus. Oh, okay. Oh, this is great. So let me do this.
Well,
Okay. Because this is a realizer, it's very long, so I want you to look at it. So this is the theorem we want to establish. So for any 2 points in A and any path, so the P and then followed by this type. So it's a path in A and between two endpoints, A, right? So now you have a P between P.
what's the curly brackets underscore?
It means that because the path can be dependent, and this is not, the A is not depending on
Right.
the position. So it's a constant. Right, and then there's a path I and the path, so it's a path of path. I don't really want to go into detail why this makes sense, but this believe me, this will be a square with a P this side, P this side, and a constant on these two sides. And then, all right, so everyone get a rough idea of what's going on here. And so that's a theorem, and we want to prove it. I already wrote down the realizer because I think if I live demo it, I will make typos on there. So I guess a minus will work. Oh wait, what should I think the font?
Control X minus.
So I did that.
Didn't work.
Oh, whoops.
Things can only get bigger in Emacs.
Okay. Okay. Anyway, let me go down. So this, if you work it on paper, it's just a three-dimensional composition problem.
But how did you get this? Can you? I mean, don't obviously do it in front of us, but you didn't, as it were, just type this in, right? Presumably, Red Pill helped you in some way to get this, right?
Yeah, the vertical compare now, for example, like something is not well typed, and I change all of it till that is okay. Yeah, unfortunately, in that process, I'm afraid I was taking too much time, so I didn't show that. But I can show other things to convince all of you to that we are really doing some kind of checking here. We're not just outputting yes. All right, so this is a realizer. So it's just an HCOM of HCOM. I don't want to explain why this works, but anyway, there's the realizer for this. So once you prove this, then you have an auto. So I also put in a print here so you can see the realizer. So the way to run it is that, okay, so now it's run. Right now the interface is very primitive. Please bear with us that we didn't even spend any time on this yet. But you can see that, okay, it says that it's proved, but it's really not informative. So let me change something here because auto is probably too powerful for the purpose of teaching. So let me change to auto. Oh, actually, let's just pretend that we didn't use anything and to see what's going on there. So basically, it's asking now, how should I prove that this is in the right type? And it's basically just a copy paste of the theorem statement. So let me do something like, what if we do one step auto? So there's something called cut. All right. So this is basically like applying one level, like one round of the invertible rules and then stop. And the question mark is, well, print out something, like print out the current state. So if you look at the goals, you can do that, I guess you can't. Should I cross?
Agreed.
Okay, I don't know how to, okay. Sorry of the font issue. I hope you can see it. Do you see my cursor there? So for the first goal, for example, it's trying to prove that A is in, like A is in A. So A is a cat. Alright? And then this is basically saying that the first two phase, is in the right type. And then there are also adjacency conditions that you, like for any combination of the two, you have to make sure that all the two fit together. And there are some of them, let me just skip this part. And then eventually you also have to show that A, the cap, there's also an adjacency condition between the cap and the tube. So you also have to make sure that under that restriction they're also the same. Basically, I want to make sure that the entire box fit together. So there are lots of cases that you check every adjacency condition. And so this is the adjacency condition. And after that, well, as I said, you also want to make sure that A is a type. That it makes sense to talk about membership in A at all. And then there are other things like, what's this for? Oh, so this is some of them is showing that suppose this HCOM is okay, that is coherent. How do I even know that it's in the square type that I just write on there as a theorem? In the theorem I say that there's a path of path, and I claim that this realizer is a realizer of this path of path. So in order to be a member of path of path, and also you also know that, well, for example, it's a path between A and B, then if I plug in 0 for this entire realizer, then it should give me, it should match the 0 side of the type. Okay, so I don't really expect you to read this at all. I just want to convince you that we are not just outputting yes.
But I'd like you to scroll right to the bottom of that buffer.
Okay. So,
I just want to see how many goals there are.
oh, okay. There are lots.
There are quite a lot, aren't there?
So all of them can be solved automatically, it's just that I stop them after one. Yeah. And also there's
Okay.
yeah.
So what do you do next? Do you choose one of them and solve them, and then choose another one, or do you just say, "Oh, I should have said auto"?
In this case, I think you should say auto because all the invertible rules
Yeah.
in our design principle is that the machine can figure it out, and the user probably shouldn't access the primitive rules. If they are invertible. For non-invertible rules, I think then we can allow users to do it. For the invertible rule, I think we should just apply it as soon as possible. All right.
This is red pill, so the user should have the right to access anything, right?
Okay, so we haven't. Yeah, maybe eventually yes, because you can. I didn't demo it, but you can also write the derived rules or derived tactic based on primitive rules. So you can just trust the code and then write your own tactic. But that mechanism is not fully developed. We have some ideas. It's still very new, so all the advanced features are not there yet. For example, the new port support the structural editing. I'm not sure if we want that, but anyway, we don't have that. All right. So, okay, so you can look at oops, not this one. So we have been working very actively on the RevPro, and you can follow us on GitHub. Okay, let's go back to the presentation. So the conclusion is that we have a typical extension of the RevPro realizers, and we have so far we maintain the canonicity on points. So this is different from CCHM. So for example, points in a circle will only be base. They will it's impossible to have the conv with empty system or something like that. We're still working on the conv universe and balance, and we're also working on the RevPro and hoping that one day will be a fully working proof system with a very nice user interface. And we want to put a acknowledgement here. So our work is strongly influenced by lots of work that actually many are not given by people sitting here. We are especially influenced by the VCH and CCH paper, the cubical thing. And we're also influenced by the work by Danny Cotta and Gian. And they also work out some form of the cubical type theory. And we also take ideas from them. And I'm not able to list exhaustive list all the very inspiring discussion that we have in person or on the mailing list and so on. So yeah. Anyway, so this is my presentation, and thanks for your attention.
Any questions?
Which types are implemented in RedPearl?
What do you mean?
Which types are already implemented in RedPearl?
Let me look at it. Dependent function, dependent pairs, we have two kinds of bool. The circle, I think, is implemented, but it's not really tested.
Okay. And you have identity types, right?
Oh, we have path. Yes, yes, we have path. That's the demo. Yeah, and also I'm
Sorry, identification types.
but we are not even calling that in RedPearl anyway. We are calling path.
Good.
Yeah, there's an issue that whether calling
Whether
identification,
they are.
meaning that you also want the J that computes on
Yeah.
level. You can have a realizer for J, but that realizer doesn't really compute on constant path.
So you have a propositional version of that.
Yes.
So if you have a type that's like a degenerate line, so it doesn't actually depend on the variable, and you coerce along it, does that always give you whatever you fed in at the other end?
No. I believe that if you allow it unlimitedly, you'll end up with regularity again.
But then isn't that just an empty comp, essentially?
For the universe, yes.
So you still have some empty comps.
Okay, so because we kind of doing a separation, so after the separation, there's no empty system. Maybe I should say that. But our code is not perfect in the sense that it doesn't have all the regularity you have, that all you wish to have. I think it's difficult to have your property you want. If the coercion on the constant type, then you'll end up with the same thing. I don't think it's possible. You can prove that in the spatial case, for example, in the circle, in bool, it's a case that if you coerce along a constant type, then it will be the same thing. In general, I think it's very difficult to achieve that for every type. Any other?
Is there a presentation of this model as a CWS thing?
We haven't. Yeah, they're talking about the categorical semantics.
Yeah.
We haven't think about that, and I'm not the expert in the category theory, so I'm really not able to answer that. But we do wish that eventually, if there isn't a category theoretical semantics yet, then we do wish that someone will work on it. Because how do I even know that the circle we define is the real circle? And we really need to interpretation of this circle into some other models to compare with the classical definition.
Well, how do you even know that it's an interpretation?
You can interpret the value part, I think, and leave all the computation to the programming language system. I think we can talk about it later.
Okay, thank you very much.